Hello, this is Coach McGaw, and I'm going to go over what we're going to go over in class, physical properties. This is for September 14th and 15th, the A and the B days. So if you missed those days or you want to go over this material again, that's what this video is for. I'm going to share my screen here. I'm going to just use first period because it's convenient. Remember, we got our launch Zoom meetings at the top. By the way, your Zoom meeting's going to be the same from now on, the link, at least through October 2nd, because our schedule's remaining the same. There is a new assignment up, physical properties assignment. You can click here to get to the assignment, or you can click in classwork. Okay, everything for a grade is up here in the classwork section, in case you need to look at that. Then I have also added some things to the Bitmoji classroom. Okay, go to present. And this time they're on the whiteboard. Remember, anytime you see that finger pointing, that means there's something linked there. Right now it's all videos. Okay, make use of these materials. This is extra instruction if you need it. And it's designed to be in addition to what we go over in class. And just a reminder, I found this really good video on how to rename yourself in Zoom. Okay. So some of you are still logging in with only your first name, and one day it's going to cause an attendance issue for someone. I'll have to guess which Andy is it, and I may guess the wrong one. Okay, today we're going over physical properties. This should be review for most of you, but hey, if it's not, that's okay. Never hurts to be reviewed, never hurts to hear it from the first time. So, what are physical properties? The color, the shape, the mass, magnetism, whether it's magnetic or not, texture, whether it feels rough or smooth. Physical properties are things you can measure without changing the substance. It remains what it was before you started. Okay, this is a video about how we use physical properties. I know the gentleman in this video repeats himself a lot, but it's a substitute for a lab we could do. So we're going to go ahead and at least watch parts of it.
Hi, I'm SRS, and in this
Gonna skip to some of this
placement test where we put the object in to a liquid and then measure the rise of the liquid, that displacement is then the volume of the object that was submerged. Before we do that, we need to find out, is it going to react with water or is it going to dissolve in water? So in order to do that, we're gonna start with a solubility reactivity test. So we're going to take a small piece of the sample and put it into a test tube, put 2 small pieces in. And we're going to put just a little bit of distilled water in to see if there's any evidence of a reaction. So there's no bubbles forming, there's no precipitate forming, none of the evidences of a reaction. So we'll give it a little more water in and see, nothing seems to be happening. So the next thing we want to determine is it going to dissolve? So I'm going to put a little bit more water in, and in order to agitate it without spilling it, I'm going to put a stopper on it. I'm going to let it sit for a moment. And then again observing, I see no evidence of it dissolving or reacting. So I'll agitate it gently. And there seems to be no evidence that it is dissolving. So we're going to begin by saying that it is not soluble in water and it does not readily react with water. So those are the results of our first 2 tests, which we need to know those results before we carry on with the other test, that is the displacement test. So in order to find the density, we need to find the mass and divide it by the volume. So we're going to use a scale, and this scale reads to the 1/100th. The mass will be in the results section. So having recorded the mass of the sample, we're now ready to move on and find the volume of the sample. And we're going to do that with the displacement method. And so we record the initial volume of the liquid, and then we're going to put the sample in and record the final volume. Then the volume of the sample will be the difference between the final volume in the graduated cylinder and the initial volume. And it looks like this. We're going to take the sample and we're going to carefully put it into the graduated cylinder. We're not going to drop it from up high because it's glass. We don't want to break it. And now that's going to raise the level of the liquid, and we're going to take that final measure and subtract it from the initial measure, and that's going to give us the volume of the sample. So that's the procedure. So let's review real quickly. First, we find out with regards to the results, then solubility with water, we did not notice any solubility, any dissolving. So that we're going to say is not readily soluble in water. And with regards to reactivity with water, also not readily reactive. We did not notice any reactivity in the course of the experiment. With regards to the mass, we put it on the scale, and here are the results from that. 31.36 grams is the mass that we came up with. So that's going to be your mass for the sample. With regards to displacement, our initial volume was 30 milliliters. Exactly. We set it up that way on purpose. We made it 30 milliliters to start with so that it would be easier to determine the volume. Now, after we put the sample in, we had to find the final volume, and it was a little between 34 and 35. It was a little bit between 34 and 35, and extrapolating the lines on the graduated cylinder, I'm going to call this sample having a volume of 4.33 milliliters, which is cubic centimeters cubed. So we're going to end up with a volume of 4.33. So we have a mass of 31.36 and a volume of 4.33. In the conclusion, we will calculate that and discuss what that means. The next result would be the magnetism test. And as we said, as we approach the sample with a magnet, will it or will it not, do that attraction thing that is so red because it's a very strong magnet. So it does not attract magnetically. So we would have to say that the characteristic of magnetivity is it is not magnetic. It is not magnetic. So those are the 4 tests. We're going to take those tests and do our best to come up with an answer as to what this could be. So the next thing we do, we'll in our results, we're going to take our results and go to a table, and I'm going to Google density of metals, known density of metals, and we'll come up and see what we come up with. And we see here's a chart, and we can go through the chart until we find something that has the number that we came up with. We'll look at that in the conclusion section. Then we're going to compare that, whatever that metal that comes up, we're going to say, well, is that metal soluble in water? Just Google, is whatever you think it is soluble in water, yes or no? Is that metal reactive with water, yes or no? Ours was not. In this case, ours was not. So if you find something that matches the density but is reactive with water, that thing cannot be the thing that reacted with water because our sample did not react with water. Same thing with magnetivity. If you find, if you were to find that, it was stainless steel, if your density, stainless steel is magnetic whatever this is. This was not. So the results of the magnetivity test would rule out whatever this is made out of. All right, let's move on to the conclusion. Again, we said, you know, that the results for reactivity and solubility was not, it is not, magnetivity not, and the density. So we calculated a mass of 31.36 grams and a volume of 4.33 cubic centimeters. And this results in a density of 7.24. So now we go to the density table. So looking at a density table, we find that the expected density of 10 is 7.28. So using that as our starting point, we're now going to apply the results of the other tests, because 7.24 is pretty close to 7.28. And if we apply the other things to it, we're going to find that 10 is not soluble in water, 10 is not reactive with water, 10 is not magnetic. So the last step in this conclusion phase is to compare our sample to known examples of 10. And if you have a sample display.
Okay, like I said, he repeated himself a lot, but it does illustrate the point that that's what we use physical properties for. We use physical properties to identify things. Okay, now the difference between physical changes and chemical changes: physical property, you chop the wood in half, it's still wood. You burn something, you combine it with oxygen, it turns into something different. Okay, a chemical change causes it to become something different. All right, now the density of matter. Density is mass divided by volume. The more tightly packed the molecules are, the greater the density. Okay, this is not very dense. This one is more dense. Okay, now volume, since we've talked about, we'll talk about mass later, volume is the amount of space an object takes up. All right, now this is low density, this is high density. They take up different amounts of space, they have different volumes, but they have the same mass because they're balancing each other out. But this object takes up more space than this object, although their masses are the same. Now, one of the more complicated things they want you to know is viscosity, and it's only the word. Don't get hung up on this word viscosity. It just means how fluid something is, how easily it flows. Honey flows really slow, water flows really fast. Honey has a high viscosity, water has a low viscosity. Now, one thing that's counterintuitive here: water flows fast. If it flows fast, viscosity is low. Okay? If it flows slow, whatever this is right here, it's flowing really slow. I mean, look at this. This thing's already filled up a third of the cup, a fourth of the cup. This thing hadn't even hit the bottom yet. This flows really slow. It's got a high viscosity. Now, these guys here, I'll skip a lot of it, but they do demonstrate viscosity very well in this video. This is something I'd like to do in class, but since we're on virtual learning, I'll show you the video.
Today on site.
Okay, skip to where they get, skip past all this. That's kind of not interesting. Okay,
in the first heat of our race, we have water, rubbing alcohol, and cream. Water finishes first with a time of 0.233 seconds, and rubbing alcohol finishes last with a time of 0.4 seconds. In the second heat of our race, we're going to be racing olive oil, lamp oil, and vegetable oil. Lamp oil finished first with a time of 0.467, and olive oil finished last with a time of 0.633 seconds. In the final heat of our race, we're going to be racing honey, maple syrup, corn syrup, and dish soap. First across the finish line is maple syrup with a time of 1.33 seconds, followed by the blue dish soap with a time of 4.633 seconds. And then slowly but surely, the great corn syrup crosses the line with a 19.5 seconds. And then finally, honey with a 20.767 seconds. Here are the results of our race. Water crossed the finish line first, meaning that it has the highest flow rate and the lowest viscosity. Honey was last across the finish line, meaning it has the lowest flow rate and highest viscosity. Let's look at this experiment a little closer. All substances...
Okay, the rest of it's irrelevant to us right now. Now, some things to ask yourselves. What are some things with a high viscosity, meaning they pour really slow? What are some things with a low viscosity, which means they pour fast? Water, as you saw in the experiment, has a very low viscosity. Water pours very easily. Okay, now buoyancy. Buoyancy, first of all, is spelled funny. I always spell it wrong and have to use spell check. B-U-O-Y-A-N-C-Y. It just means if something floats or not. Buoyancy is a fancy word as if something floats. If it's less dense than water, it floats. If it's more dense than water, it will not float. Okay? So this basketball is floating because it's less dense than water, and largely because it's filled with air. The pebble sinks because it is more dense than water. All right? That's what we mean by buoyancy, is whether or not it floats. Now, one you're a little bit more familiar with, at least in terms compared to viscosity, is conductivity. It's how easily electricity and heat goes through something. All right? So what are some things that are conductive? Earlier today, someone said copper. Yes, we use copper wires in our homes to get electrical power into our homes. Okay? Metals tend to have a high conductivity. Electricity and heat go through them easily. Metals are good conductors. Silver is actually the best. Now, why don't we use silver wiring? That would be very expensive. So we use copper wiring instead. This is why we cook in metal pans. The heat goes from the stove to the food very quickly. To cook something, we want to do it in something that conducts heat very well. Now, the oven mitts are just the opposite. They have low conductivity. This pan has been in that oven. It has conducted heat to the food very well. It has gotten very hot. We don't want to touch it with our bare hands. So we put up on our oven mitts, have very low conductivity, so we can pick up that pan, carry it to the table, and set it down to where it cools off. The oven mitts are called insulators. Insulators are things which do not conduct heat and electricity well. And that's why we have a shielding around wires to insulate our copper wires so our electricity does not heat up our house or shock someone who's not aware that it's there. And our oven mitts protect us from picking up hot objects. Now, boiling point. We've talked about this is vaporization. This is water changing from a liquid to a gas. And if you remember what we said, when things are vaporizing, when they're going through vaporization, the temperature does not change. So that boiling point stays at a constant temperature. The stronger the bonds, the higher the boiling point of a liquid will be. Now, we're not talking about bonding until a little bit later. Actually, we'll talk about it later this week. So just keep in mind, the stronger the bonds in something, the higher the boiling point. Now, the higher the boiling point, the lower the freezing point. This substance over here has a higher boiling point, so the freezing point will get lower. All right? And it's for the same reason, for the nature of the bonds. Now, mass. Mass is just how much stuff is in something. Mass is the amount of matter. Matter is just stuff. Specifically, it's atoms. How many atoms something is made out of? It's the mass of it. I want to pick this up now. We're going to talk about it again second semester. But for now, I want you to know mass is not the same as weight. Your mass, the amount of atoms that make up you, is the same everywhere you go. Your weight changes because weight is dependent on gravity. So if you were going to go from the Earth to the moon, you would weigh approximately 1/6 as much on the moon because the gravity on the moon is less. Your mass would be the same, okay? Because the number of atoms that make up you would be the same. So what is the difference between mass and weight? Mass is just how much stuff is there. Weight is the pull of gravity on that stuff. We use these interchangeably because unless you're an astronaut, you spend all your life on Earth, okay? But we do need to be aware that if you were ever to leave Earth, your weight would change, your mass would stay the same. Talk about this briefly, the law of conservation of mass in things that happen in ordinary chemical and physical changes. The amount of mass stays the same, okay? There's 31 kilograms on this side of the reaction. There's 31 kilograms on this side of the reaction, okay? Mass is not created, it's not destroyed when we do common chemical and physical changes. Now, because we've been talking about physical properties, we need to talk a little bit about chemical properties. Chemical properties, whether it's flammable, whether it will rust, whether it's corrosive, its reactivity, chemical properties change something. When something goes through a chemical reaction, it becomes something different. That's why we cook things. When you burn things, when you heat them up, they become something different. So reactivity is how easily something chemically reacts with something else. We saw that earlier, that the tin was not reactive with water. Okay, that's a chemical property. But there's 3 metals here, and it just gives you an idea of reactive. All 3 metals they're going to use in this react with water, but notice they don't all react with water the same. You can be a little bit reactive, and you can be a lot reactive. And this video is just to give us an idea of what reactivity is.
Here I'm working with some lithium metal, very difficult to cut. I've got a piece of sodium here, pretty easy to cut. You notice when I cut through that the fresh sodium is very shiny compared to the rest. Let's zoom in real quick. Let's see if we can really get in there. So this side will reflect a lot of light. The other sides are pretty dull. And you'll see that especially with the potassium here. I'm going to go ahead and give this kind of a half cut. So for the potassium, this is the side that's been freshly cut, and you can see the dullness to the other sides compared to that one. So I'm going to go ahead and take those 3, and I'm going to add them to water, and we can look at the kind of reactivity of those 3 alkali metals with water. So here I'm going to take the lithium and add that to the water. It's going to generate hydrogen gas and lithium hydroxide. So you're going to see a pink color develop here, and then you're going to see some smoke come off, and that's either lithium metal or that's lithium hydroxide coming off of there. Maybe a little bit of liquid water. But it's not as reactive as, say, sodium, so I'm going to put sodium into the next one. And the sodium is actually probably going to ignite. So you'll see some orange flame perhaps, or some sparks, or some shrapnel. And then the last one, I'm going to go ahead and put my 2 pieces of potassium in. So that cut it in half. So this is less potassium than the other 2 in terms of amount. You'll find that the reactivity is a little bit greater. Now that potassium there was quite reactive there.
Notice that the third one reacted just in a matter of seconds. It had more reactivity than water than the other 2. Okay. Chrome is not reactive, but this iron piece is very corroded. They've been exposed to the same condition. Non-reactive with oxygen in the atmosphere, reactive. Okay, that's pretty much it. Remember, you can watch this as many times as you want. I leave the Google Slides presentation online and refer back to this whenever you need to. Thank you.